My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 574. In this lecture, we will try to understand Adagrad, that is adaptive gradients, in our SGD and SGD plus momentum. In both of these algorithms, your learning rate, which we are calling it as eta, is often set to a small number 0.01 and things like that, and the learning rate is same for each of your weights. So let's assume you have multiple weights. Remember, whenever I say W in all of our discussions, what I mean here is WKIJ. So what's happening literally is, for each of my weights or each of my parameters, I have same eta. I have same learning rate. So the key idea of this new algorithm called Adagrad, which basically has an adaptive learning rate for each weight. The key idea is each weight or each parameter of your optimization has a different learning rate eta. This is the core idea. This one, what is the core idea? Each weight or each parameter of your optimization has a different learning rate eta. Again, you may wonder why it is important. Oftentimes, what happens is, in your original data set, you may have some features which are sparse, some features which are dense. What is the sparse? The sparse feature means only the few times you will see features to be non-zero. That is sparse, isn't it? Like if you think of like bag of words, just try to recall, we discussed bag of words, isn't it? If you think of bag of words representation, it is very sparse representation, while if you think of word to vec, what is word to vec representation or dense feature? Dense feature basically means the most of the values for given feature are non-zero. That is dense feature, isn't it? Sparse basically means most of them are zero. That is sparse. Only few of them are non-zero in the case of sparse. So sparse features tend to have different behavior as compared to dense features. So when your data set has sparse features keeping or having same, when your data set having, what is this sparse features? We already discussed. So when your data set has sparse features keeping or having a single learning rate for all of your weights is not good for optimization. And the most important idea to resolve this issue, is the idea of Adagrad, isn't it? You are trying to create different eta, different learning rate, and also called as adaptive learning rate, and one learning rate for each weight or for each parameter. So let's start with simple SGD. How does simple SGD can look like? Just try to recall. Your W at time t is equal to W at t minus 1 minus eta into GT. This is your simple SGD. Now with Adagrad, what we'll do here is, we will say, in the case of Adagrad, your Wt equal to Wt minus 1 minus eta dash of t into gt. Now note that this eta dash t there is a different eta dash for each weight and at each time, at each iteration t. This learning rate now has become adaptive. That is important. This learning rate now has become adaptive. What it means? What it means is that you have a different learning rate. Means eta, just think about eta, which is always constant. Eta in the case of HGD, in the simple HGD, you have eta. In the case of HGD, your eta, which is always constant. That is important, isn't it? Which is same for all weights, isn't it? Eta dash t changes, your eta dash t changes for each iteration. Now, the question here is, what is this eta dash t? Let's define eta dash t as, what is my eta dash t? My eta dash t as eta by under root of alpha t minus 1 plus epsilon. Here eta dash t is different for each weight. There is a different eta dash for each iteration, it changes. This eta is a constant here. Let me say your eta is like 0.01. The epsilon is, what is this epsilon? This epsilon is small positive number, just like 10 power minus 4. Let's assume if alpha t minus 1 is 0, if this is 0, if your alpha t minus 1 is 0, if this alpha t minus 0, you don't want to have division by 0, isn't it? So we are creating this epsilon in the denominator to avoid division by 0 problem. It is very small, this epsilon, it is very small, a small value that can add here just to avoid dividing by 0. If alpha t minus 1 becomes 0, or if it is 0, you don't want this to become, you don't want this to become division by 0 problem. Let's just understand this. What is my eta dash t? Eta dash t equal to under root of alpha t minus 1 plus epsilon. What is my alpha t minus 1? Your alpha t minus 1 is summation I equal to 1 to t minus 1 gi square. What is my gi? Just try to recall. My gi is derivative of L with respect to W at I minus 1th iteration, isn't it? Iteration. Gi is the gradient term. What is my gi here? Gi is gradient term. So what are you doing here? If you look at the whole story, what we are saying here is this update equation. Which update equation? Just see this update equation. Wt equal to, let me show this update equation. Which one? Just see this update equation. Wt equal to Wt minus eta dash t into gt. This is update equation of Adagrad. This is update equation of SGD, isn't it? If this update equation means Adagrad update equation looks very similar like SGD update equation, except that my learning rate eta dash t is different for each weight and changes with each iteration, isn't it? It changes with each iteration. How does it change? My learning rate for each weight at each iteration is some constant, and what is my learning rate here? My learning rate eta dash t is equal to this one. This is eta by, what is this? Eta by my learning rate is for each weight at each iteration is some constant. What is this constant? Just like 0.0 divided this by some number alpha t minus 1 plus epsilon under root of this one, isn't it? What is this alpha t minus 1? Alpha t minus 1 is a gradient, isn't it? Alpha t minus 1 is gradient, which is square, always positive, Alpha t minus 1 is summation of I equal to 1 to t minus 1 gi square, which is always positive, which means alpha t minus 1 is positive. That's what we are saying. It is summation of squares. Therefore, alpha t minus 1 is always positive, as it is summation of I equal to 1 to t minus 1 gi square. It is sum from first iteration to t minus 1th iteration. So, what are you computing? You are computing, what are you computing here? You are computing g1, g2, isn't it? Just say this one. What you are computing here? Here you are computing g1, g2, g3, so on, gt minus 1. Just say g1, g3, so on, gt minus 1. We already had these gradients. At a tth step, suppose at a tth iteration, we computed gt. Isn't it? At tth iteration, you can always calculate gt, isn't it? At tth iteration, suppose what we computed gt also. By adding up of all of the squares of the gradients, you will get alpha t minus 1, which is always positive. And also your alpha t minus 1 is always positive, and also this alpha t minus 1 is positive. Alpha t minus 1 is greater than 0, and also as iteration number increase, which means as t increases, your alpha t also increases, because you are summing up positive numbers. T basically, what is your t? Basically means iteration number. So as iteration number increases, your alpha t minus 1 increases. Also just say as iteration number increases, your alpha t increases. Your alpha t is always greater than or equal to alpha t minus 1. Just go through these points. Just try to understand what is your eta dash t, what is the difference between, this is related to Adagrad, this is related to Adagrad, and this one is Adagrad, this is SGD or SGD with momentum. What is the difference between these two update equation? I request all of you to go through this particular lecture, so that I will continue my discussion on Adagrad in my next lecture also, that is lecture number 575. Thank you very much.